Welcome to section 4.3. We're going to be discussing rules of logarithms. We've already discussed that logarithms are inverses of exponential functions. We've been looking at rules for exponents. They've been popping up since we've been in chapter 4. Rules for exponents, we reviewed these at the beginning of the semester, and we're continuing to expand on that concept. I'm starting out with inverse rules. The rule states that if a is greater than 0 and a does not equal 1, then the log base a of a to the x power equals x, and a raised to the power of log base a of x equals x. And that's for x greater than 0. Now, what in the world does that mean? You probably didn't quite grasp what we just read. We know that since exponential functions and logarithmic functions are inverses of one another, just like if you take, we discussed this in the previous video, if you take the cube root of x and then you've got the x cubed function, if you put one inside the other, they cancel each other out. So the cube root of x cubed is going to give us x, and they cancel out because they're inverses. So this is just the notation that you're having to get used to here, but it's the same concept. So in part 1, we're doing the logarithm of an exponential function, and they have the same base, so they cancel each other out, and they just leave us with that x. In part 2, we've got an exponential function that happens to have a logarithmic function for its exponent. So all that log base a of x is all in the exponent of the original base a. And they both have the same base, just like in part 1. So they also will cancel each other out and just leave us with the x, with the inside of the log function. That's all that's going to be left here. So that's all that these rules are stating. You're just having to get used to this notation. Let's look at example 1. We're asked to simplify each expression. Part A, we're going to calculate e to the ln of x squared power. Remember, e is that irrational number that we discussed in section 4.2. We know it's approximately 2.71, I believe. Let me double check on that. I think that's right. Yes, it's approximately 2.718. But e is just an irrational number. And also remember that natural log means log base e. So what you really have here is you have e raised to the log base e of x squared. And since these have the same base, they're inverses and they cancel each other out. So what do you think is going to be left? My answer is going to be this x squared that was inside my log function. That's what's left over. In part B, we've got log base 7 of the exponential function 7 to the 2x minus 1 power. Again, notice they have the same base. Now, if they did not have the same base, we couldn't just cross them out. It's only because they have the same base. Because they have the same base, we can cancel these two guys out, and the 2x minus 1 is going to be our answer. That's all that's left. Okay? And that's it for that part. We've got a number of rules for logarithms that we're going to be working with in this section and in the next section. The first one, several of the rules that we're about to discuss are like a counterpart to the exponential or the rules for exponents that we've learned in the past. You should remember when you're working with rules for exponents, you've got a rule that states if you've got a base to a power multiplied by that same base to another power, so a to the m times a to the n. Do you remember how we handle that situation? If you're multiplying like bases, you keep the common base and you add your exponents. Well, the logarithms being the inverses of the exponential functions, they have a very similar property. So we have a product rule for logarithms that states for m greater than 0 and n greater than 0, log base a of m times n, so that's multiplication, equals log base a of m plus log base a of n. So if you're taking the logarithm of a product, this can be broken apart as the logarithm of the first factor plus the logarithm of the second factor. Example 2, we get a chance to practice this. It states write each expression as a single logarithm. So in part A, we're given log base 3 of x plus log base 3 of 6. So we are actually starting on the right side of this equation over here. We've got two logarithms that are being added, and they both have the same base. And just like in the rule and the property, we have to have the same base in order to put them together into a single logarithm. But because they have the same base, we can say that this is log base 3 of x times 6, which we can just write as 6x. And I can stop there. That's all I have to do. I've written it as a single logarithm. In part B, again, we're starting on the right side of our rule over here. We've got separate logarithms that are being added, and what is our base in part B? We've got natural log of 3 plus natural log of x squared plus natural log of y. Again, we know that natural log means log base e, so that means they all have the same base. So we can combine these. We're going to multiply the 3 with the x squared and the y inside our natural log function. So we want to say natural log of 3 times x squared times y. Or I can just simply write that as the natural log of 3x squared y. And that's it. I'm done. So I've used my property. I wrote them as a single logarithm. And that's example 2. Now we're ready to go to the next page. Alright, so you're probably not surprised that the next rule is a quotient rule. So it tells us how to handle logarithms of fractions. For m greater than 0 and n greater than 0, log base a of m divided by n equals log base a of our numerator m minus log base a of n. This is similar concept as your quotient rule for your exponents. Okay, so remember, for the exponential rules, we had the property that stated, let's see, I think like maybe a over b to the m power was equal to, is that the right property? I'm sorry, I'm sorry, that's not right. That's not what I wanted to say. If we've got a to the m over b to the m power, oh, no, I'm sorry, that's still not right. I'll get it together here in a second. If I've got a base a raised to a power m, and I'm dividing it by the same base raised to a different power. So sorry about that. It took me a minute to get my head straight there. So I'm dividing like bases, and I have different exponents. Remember, we've got a property that tells us we can keep our common base and subtract our exponents. So that was from the rules for exponents that you've been working with since Algebra 1. So this is like the logarithmic counterpart to that rule. Let's look at example 3. We're going to practice using that quotient rule for logarithms. It says write each expression as a single logarithm. Part A, we have log base 3 of 24 minus log base 3 of 4. We are asked to put it together into a single logarithm. Since these have the same base and they're being subtracted, we're going to say that this is log base 3 of, and inside I'm going to put my 24 in the top, and I'm going to put my 4 in the denominator. So 24 over 4. Now, of course, this can be simplified, and we need to simplify it. 24 divided by 4 is going to give me 6, so this becomes log base 3 of 6. And that's it. For part B, natural log of x to the 6th minus natural log of x squared. To put these into a single logarithm, we're going to do this basically the same thing. Where they're being subtracted, so we're going to have a fraction inside our log function, and the numerator is going to be x to the 6th. The denominator is x to the 2nd, and it does need to be simplified. X to the 6th over x to the 2nd. We get to use that same exact rule that I talked about up here. They have the same base. So the rule is we keep the common base and we subtract our exponents. So we have natural log of x to the 4th power. And we're done. We can stop right there. Now, it's okay if you stop here, but sometimes, nope, we're going to stop right there because we didn't talk about that yet. So I'm just going to keep right on going. That's it. Natural log of x to the 4th. that exponent that we got, that 4, can be written in another form, and we're going to see that in our next rule for power rule for logarithms. The power rule states that for m greater than 0 and any real number n, log base a of m to the n power equals n, so that exponent is coming to the front as a coefficient, so it's going up here, times log base a of m. Alright, so our exponent is going to go to the front as a coefficient, and we're just left with this log base a of, and then whatever value we had in here without the exponent. Now, where do you think this rule is coming from? All this is a combination of, well, we're going to do just a little bit of arithmetic here, I guess you could say, or a little bit of algebra. So I'm going to just make up an example to show you why this works the way it does. So let's say I've got log base a of x to the 3rd power. According to this rule, I should be able to write this as 3, bring the 3 to the front, times log base a of x. Alright, but why does that work? Well, I'm going to look at my x to the 3rd. I just want to see what happens if I play around with my rules for exponents. So I can write this as x to the 3rd with the exponent on the inside, and that's going to give me log base a of x times x times x. According to my first rule for logarithms, the product rule, I can write this as log base a of x plus log base a of x, and I apologize, I'm running out of space, plus log base a of x. Okay, so what I've done here is the x to the 3rd, I wrote it as x times x times x, and now because I'm multiplying these together inside my function, my product rule for logarithms, or property 1, rule 1, tells me to break it apart by adding each of those individual factors. So log base a of x plus log base a of x plus log base a of x. Alright, this can be simplified because this is the same thing being added 3 times. So this means 3 times log base a of x. And there you have it. 3 times log base a of x, that exponent that used to sit up here has now been moved to the front. So this rule is just a kind of a combination of the product rule for logarithms and just what basic facts that we know about exponential functions and what they mean. Let's look at example 4 so we can practice using our rule. Example 4 says, rewrite each expression in terms of log of 3. So that's asking us to write each of these so that we've got log of 3 in our answer. In part A, I can use my power rule to bring my 8 from the exponent to the front as a coefficient. So I can write it as 8 times log of 3. And I've done what I was asked. This is writing it in terms of log of 3. This is 8 times log 3. In part B, I've got log of the square root of 3. Before I can use my new properties on this, I need to do something about that radical. I don't want to leave it as the square root of 3 because I don't really have a rule that tells me how to handle a logarithm with a square root. But I can rewrite this. I know that this is the same thing as the log of 3. The square root, remember, is the 1/2 power. If you don't remember that, you need to make sure that you know it. Square root of anything means the same thing as raising that base to the 1/2 power because your exponent is a 1 and your index is a 2. Now that I've got the log of 3 to the 1/2 power, the 1/2 can come to the front and become 1/2 times the log of 3. So this is just my power rule again that I'm using. So I've written it in terms of log of 3. Part C, to complete this one, I still need to go back and look at rules for exponents. So those rules for exponents are not going away for us. This 1/3, 1 over 3, that's 1 over 3 to the first. So that 3, I can put it into the numerator and I just change the sign on my exponent. So this will become log of 3 to the negative first power. And then this exponent will come to the front and become negative 1 times log 3, or just negative log 3. Okay, so those are my answers there. On my next page, I've got a summary of all the rules that we are going to be using for logarithms. some of these you may not necessarily need, but it's just kind of getting them all together. If you recall, your rules for exponents had 8 rules. The rules for logarithms, we've got 8 rules for those as well. Let's start with number 1 and go through these. Number 1 states that log base A of A equals 1. Alright, you could if you want, there's different ways you can think about this, but let's look at the inside of our log function. We've got this A. We don't have an exponent on it, so we know it means A to the first power. So you've got the log base A of A to the first. Since these have the same bases, you get to cross them out because they're inverses. So the only thing that's left is that one exponent from the A. In part 2, or in property 2, log base A of 1 equals 0. I would just think about this one in terms of, we know that we can convert this to exponential form if we do the loggy froggy. So A to the 0 equals 1. Alright, and we know that's true. A to the 0 equals 1. So log of any logarithm of 1 will always equal 0. So it's just a counterpart to that rule that we already have. Rule 3, log base A of A to the x equals x. This is just because these are inverses of each other. They have the same bases. They'll cancel each other out, and that exponent will be the only thing that's left there. And in part 4, or in property 4, same thing there. You've got a logarithmic function inside your exponential function, and they both have the same base. So the only thing that's left is the n from the inside of the log function. And then 5, 6, and 7 are the rules that we just learned. The product rule, the quotient rule, the power rule. And rule 8 is the last example that we did. It's just a matter of writing this 1 over n as n to the negative first power. So log base A of n to the negative first power, and then bring the negative 1 to the front and make it a coefficient, and it gives you your negative 1 times log base A of n. So they kind of feed on each other. It's not that there's all these different rules. It's just you can almost just kind of narrow it down to about 4 rules really that you really need to know. As long as you're pretty comfortable with your rules for exponents, the only new ones you've got are rules 5, 6, and 7, and then also maybe rule 2. And if you know those, you're probably going to be pretty comfortable with this material. Let's look at example 5. We want to rewrite each expression in terms of log 2 and log 3. So part A, we've got log of 6. So to write this in terms of log of 2 and log of 3, let's factor our 6. We know that 6 is 2 times 3. So that gives me log of 2 times 3. Now we're going to use, which of these rules do you think would make sense here? We've got the logarithm of a product, so we're going to use our product rule. We're going to write this as the log of 2 plus the log of 3. For part B, I've got the log of 16/3. I'm going to start by let's think about, we got the 3 in there, and we know we need log of 3. What about the 16? What can be done with the 16? Or maybe you might want to break it apart first. Let's break it apart first. So you've got the log of your numerator 16 minus the log of your denominator 3. 16, what do we get if we factor that? If we do a factor tree for 16 and break it all the way down, that's going to give us 2 to the 4th power. So I've got the log of 2 to the 4th minus the log of 3. And I'm almost there. I have to write it in terms of log of 2 and log of 3. So let's take this exponent, bring it to the front, and it becomes 4 times log 2 minus log 3. And we've done what we were asked. The entire problem is written in terms of log 2 and log 3. For part C, I've got log of 1/3. This is not that hard. You can go right straight to property 8 if you want to. The 1/3 is the same thing as 3 to the negative 1st. So we've got log 3 to the negative 1st. And then negative 1 comes to the front as a coefficient. So this is a power rule that I'm using now. Negative 1 times log 3. And I've written it in terms of log of 3. There is no log of 2 this time. And that's it. Is that showing up for you? Oh, I'm sorry. There it is. Example 6. Rewrite each expression using a sum or difference of multiples of logarithms. So in example 6, we are actually going to use, we're going to be using the new rules that we just learned, rules 5, 6, and 7, the product rule, the quotient rule, and the power rule. And if we look back to when we first talked about them, for example, looking at our product rule back here, the first examples that we did with these problems were we were given something that was already broken apart and we were asked to write it as a single logarithm, so to put it all back together. We're doing the reverse now. So the problems that we're getting ready to look at here give us a single logarithm and we're asked to break it apart into as many terms as we possibly can. So that's what we're doing in example 6. So for part A, I've got natural log of 3x squared over y times z. So I can write this as the natural log. I'm going to put an arrow here because I would put it under it, but I don't have much space. So natural log, I'm going to break it apart as the natural log of the numerator minus the natural log of the denominator. So I'm just using my quotient rule. Inside the first logarithm, I've got 3 times x squared. That's a product, and that can be broken apart. So I can say that this is the natural log of 3 plus the natural log of x squared. And then over here, I'm subtracting this logarithm. Now, I've got a product inside it, though. I'm going to do this in 2 steps. I'm going to write minus, and then I'm going to put a square bracket, because without it, you're probably going to get confused. So I'm putting a minus in front, and then I'm going to say that this is the natural log of y plus the natural log of z. Again, I'm using my product rule for the y times z. What can be done to simplify this further? I've got natural log 3 plus this natural log of x squared can be taken a step further because the exponent is the it tells us to use the power rule. So we're going to write this as 2 times natural log of x. And when I get down here, I'm subtracting this ln y plus ln z. I need to distribute this negative. So I'll have minus natural log of y minus natural log of z. And that's as far as I can take this. If you look at what we got for our answer and you go back and look at the original problem, just think about the placement. Think about the factors that started out in the numerator and the ones that were in the denominator, and think about the signs that you see in front of each term. I'll let you think about that. For part B, we've got log base 3, and then I could have used brackets here. So for part B, I've got log base 3 of the fraction x minus 1 quantity squared in the numerator and z to the 3/2 power in my denominator. So again, I'm going to start this by just breaking it apart as log base 3 of the numerator minus log base 3 of my denominator. And then what can I do? This 2 I can bring to the front, so 2 times log base 3 of x minus 1. Over here, my 3/2 needs to come to the front using the power rule. So 3/2 log base 3 of z. Now, how do I know when I can stop? If you've got a fraction inside your logarithm, it needs to be broken apart. If you've got a product inside your logarithm, it also needs to be broken apart. If you're left with something inside that logarithm that can be factored, for example, instead of the x minus 1, what if I had x squared minus 1? I could factor that as x plus 1 times x minus 1. And then you could break it apart again because you would use the product rule on it. But there's nothing inside my logarithmic function that can be factored. There's nothing being multiplied or divided. And I don't have an exponent other than 1. So that one is completely finished. Same thing over here. There's nothing inside that it can be factored. There's nothing being multiplied. There is no fraction inside that log function. Yes, you've got one in the coefficient, but that's different. And there's no exponent other than a 1. So that's as far as we can take it. Alright, for example 7, rewrite each expression as a single logarithm. So we're just putting them all back together again. This is like we were doing earlier, but it's just a little bit more sophisticated now. So before we can put this all together, all of our coefficients need to be either 1s or -1s. And you'll notice you've got this 3 sitting here. So I'm going to use the power rule to move it up to the exponent. So I'll have natural log of x minus 1 plus natural log of 3 minus natural log of x to the 3rd power. Now that all of my coefficients are either 1s or -1s, I'm going to put it all together into a single logarithm. This minus tells me I'm going to need a fraction. So now how do I know what goes where? I know that if I'm adding, then they're going to be put together as the logarithm of a product, so I'm going to multiply the inside. But how do I know where they go? Well, they're going to go in the top unless they've got a negative sitting in front of them. The reason for that is this is the same thing as plus natural log of x to the -3rd. So you can think of it as a plus -3 if you want to, and that's going to tell me to put it in the denominator. So I'm going to put the x minus 1 in the top. I'm going to put this 3 in the top because those are being added. And then over here, I'm adding this x to the -3rd. X to the -3rd is going to go into my denominator as x to the +3rd. If that's too confusing for you, if you want to just think of it as if there's a minus in front of your logarithm, it goes in the denominator. You can think of it that way if you want to. So the minus in front of your log, if you're writing a list of these factors as a single logarithm, the sign in front of the term will tell you where it needs to go in your fraction. So the positives went in the top, and the one that had the negative in front of the logarithm went into the denominator. And I'm going to take this just one more step and write this as natural log of, I like my 3 in the front, so 3 times x minus 1 over x cubed. And you always need to think about the possibility of your final result being able to simplify. Could I simplify anything that I have in here? No. I've got x cubed in the denominator, and I've got a 3 and an x minus 1 in the top, and they don't reduce. There's nothing I can do there, so that's my answer. Natural log of 3 times x minus 1 over x cubed. For part B, I've got 1/2 times the log of y minus 1/3 times the log of z. I'm going to start by moving these. I'm going to use my power rule to move my coefficients into my exponents. So I'll have the log of y to the 1/2 power minus the log of z to the 1/3 power. And now that they have ones or -1s for coefficients, I can write it as a single logarithm. The subtraction tells me I need a fraction bar. In the numerator, I need y to the 1/2. In the denominator, I need z to the 1/3. But it's unlikely that you're gonna be leaving your answer in this form. This is not really considered simplified if you've got these rational exponents. It's better to go another step and instead use your radicals. So you've got the logarithm of this y to the 1/2 is the same thing, and you should know, if you don't know this, you need to learn it and remember it. Y to the 1/2 means the square root of y. And your denominator, z to the 1/3, that denominator is going to be your index, so that's going to be the cube root of z. And that's my answer. So the log of square root y over cube root z. Okay, the next thing we're talking about is the base change formula. You're probably going to like this one. Most students don't generally care for formulas, but this one is going to make things really easy for you. It states that if a is greater than 0, b is greater than 0, a does not equal 1, b does not equal 1, and m is greater than 0, then log base a of m equals log base b of m divided by log base b of a. Now, you probably don't know what that meant, but all it's saying is that if you've got log base whatever of whatever, you can write that as the log of the inside divided by the log of the original base, as long as these have the same base in the top and the bottom. And we'll generally use the common log with base 10 because that's what the calculator uses. So this makes it really easy for us to calculate logarithms now. Looking at example 8, we have use a calculator and the base change formula to find each logarithm to 4 decimal places. So we've got log base 4 of 9. According to my change base formula, I can write this as the log of 9 divided by the log of my original base 4. Make sure that you don't try to simplify the numbers that you see here because they are both inside that log function. So now you can go to your calculator. Locate the log button on your calculator. Your log button sits right beside your 7. We're going to press log, and we're doing the log of 9 divided by the log of 4. And I hope you can see that. I think you can. Alright, so that's giving me see, I'm supposed to round this to 4 decimal places, so 1.5850 is what I've got. 1.58496. Rounding it is going to give me 1.5850. And I really should not use an equals because I'm using a decimal approximation at this point, so it's approximately equal to 1.5850. Part B, I've got log base 1.2 of 13.7. So the change base formula tells me to set it up as the log of 13.7 divided by the log of 1.2. That was my base. And then type it in. I'm getting 14.3559. Part C, you're doing the same thing here, but sometimes it throws students off if we throw in these irrational numbers. We're going to do the log of e squared divided by the log of pi. Alright, the calculator is going to help you. You do have to be a little bit careful when you type in that log of e squared. You're going to go log and then find your E button. Remember, E is above your LN button. So second LN, and then you're asked for a power to put in, and we're doing it to the second power. So put in your 2, and notice they've opened parentheses for you twice, so you've got to close it twice. And now you're ready to divide by the log of pi. Pi is just above this, it's on the button just above the division symbol. So here's your division symbol. The pi is above this caret button. So second caret, and then that gives you pi. You can close your parentheses. And that gives me 1.7471. Again, that's a decimal approximation, so I'll put a little squiggly. 1.7471. And that is example 8. For example 9, find an approximate rational solution to 1.03 raised to the x equal to 5. Round your answer to 4 decimal places. Alright, so we're going to do a new technique here for this problem. We don't really have all the tools that we need yet. So what we can do is, remember your logarithms are functions, just like square roots are functions. Sometimes it's appropriate to take the square root of both sides of an equation in order to solve it. And this is an example of where we're going to take the logarithm of both sides of the equation. So you can do logarithm or natural logarithm. Either one is fine. I'm going to do log of 1.03 to the x equals the logarithm of 5. So I'm applying my logarithm to both sides of the equation. If you want to make a note, you can. That's what you're doing. You're going to apply the logarithm to both sides. Just like you could square both sides or take the square root of both sides, you can do a logarithm on both sides. Now, doing the logarithm is going to help us because it's going to allow us to solve for x. We can use those properties that we've discussed to get the x by itself. The first place x needs to go is to the front of the logarithm using the power rule. So we've got x times log of 1.03 equals the log of 5. And we can solve this if we divide both sides by log of 1.03. So I've got log of 5 divided by the log of 1.03. And then you can type it into your calculator to get your answer. This is the exact form, and we're asked to give the decimal approximation rounded to 4 decimal places. So we can type that in. We want to do log 5 divided by the log of 1.03. So I'm getting 54.4487. That's my answer, 54.4487. Alright, and we're on our last example. Alright, example 10. Find the rate required for an investment of $500 to grow to a future value of $2,000 if interest is compounded annually for 25 years. So we've worked with the compound interest problems already. The first thing you need to look at when you are given a problem like this is how is the interest compounded. If it's compounded continuously, you're going to use that continuous compounding formula, or the PERT formula like we called it. But if it's not compounded continuously, if it's annually or semi-annually or quarterly or daily, you're going to use the original formula that we were given, the A equals P times 1 plus R over N raised to the NT power. Once we have this formula, we're ready to go. We can substitute, remember the $500, that's the initial amount. The future value, the $2,000, is going to go in for A. So we're going to have 2,000 equals our original amount of 500 times 1 plus, we're solving for R. N is the number of times our interest is compounded in a year. Since it's compounded annually, N equals 1. And we're going to raise it to the NT power. That's going to be 1 times 25. 25 is T. So that's how I've got it set up. So I've got 2,000 equals 500 times 1 plus R to the 25th power, just to make it look better. I've got to get the R out of this base down here. I'm going to divide both sides by that 500. So 2,000 divided by 500 is going to give me 4. So I've got 4 equals 1 plus R to the 25th power. Now to get the R by itself, we can raise both sides of this to, what power can I raise both sides of this to turn this exponent into a 1? We've talked about this before. When you raise a power to a power, you're multiplying your exponents, so 25 times how much equals 1? Let's raise both sides of this to the 1/25th power. So we're going to do 4 to the 1/25th power equals 1 plus R. Do the same thing over here, and it's just going to give you a 1. So I raised both sides put a note, raise both sides to 1/25 power. Alright, so we're almost done. The 4 to the 1/25th power, I can type that into my calculator. Showing up for you. 4 raised to the 1/25th power. Put your 1/25th in parentheses. Your calculator may not do it like you need it to. So we've got this really long decimal, 1.057. I could go on with it, but I think it'll be okay if I just go to 1.057 here. Equals 1 plus r. So to solve for r, subtract 1. Now we get 0.057 equals r. Now what were we asked in this problem? It said find the rate required. So you would use 0.057 for r, or you could also say 5.7%. And that's more likely to be the correct way that you would be asked to give your answer as a percentage, 5.7%. But that's it. That's all for your guided. That's all for your video lecture. Bring your guided notes to class with you, and we'll do some more practice on these this week. All right. Thank you.